biased stochastic approximation schemes. So it's actually more like an optimization study with applications to reinforcement learning, as we're going to see. So let us first try to recall what does a stochastic approximation scheme means. So in the most general settings from the 60s, 70s, classical settings from the 60s, 70s years ago, given by Robbins and Monroe, it's a stochastic process that tries to find the zeros of a certain nonlinear functions using stochastic queries of the nonlinear functions. So basically in the settings is that we try to iterate through a parameters called eta n's at iteration n and descend according to a certain drift, which is denoted by h etas. And in the classical settings, we assume that this drift term is IIDs, and the conditional expectation of this thing also evaluates to the gradient of a certain Lyapunov functions. And eventually, this scheme is going to tell us to find the stationary point where this gradient equals to 0. So in this work, we want to consider several realizations over the classical settings in the sense that it becomes a biased stochastic approximations. So the first realization we made is that the mean field doesn't necessarily equal to the gradient. It is relevant to non-gradient method, where it can be very hard to compute the actual gradient, such as expectation maximization algorithms. And the second realization, which I find is much more exciting, is that the drift term is no longer IID, but instead is drawn from a state-dependent Markov chain. So the relevant settings, as we see, is the reinforcement learning settings, where for example, in policy gradient method, this etas n actually corresponds to the policies that you're trying to evaluate, that you're trying to optimize. So mathematically, the settings that we are going to use is that the mean field is biased, it's not equal to the gradient, but it is correlated with the gradient of a certain Lyapunov functions that is moved. And the second assumption is that this, the xn is not IID, and it forms state-dependent Markov chains, where we have a Markov kernel controlled by the parameter itself. And in this case, the mean field is not the conditional expectation anymore, but instead the expectation with respect to the unit stationary distributions of such a Markov chain. So, and furthermore, we want to focus on studying the non-asymptotic convergence of such an SA scheme. So let me give some motivations, since we're in a reinforcement learning sessions, and I have to give some MDP descriptions. So here we look at a sort of like a toy example version of an MDP with finite states and finite actions. And so a policy here corresponds to the conditional probability that you want to take an actions given that you're in a certain state. So now you fix the policy at etas, then the state and action pairs actually forms a Markov chain with a stationary distributions, which is actually parameterized, which can actually be parameterized by etas. And the policy optimization problem is that we want to find an etas that maximize the average reward. So of course, evaluating the gradient of that average reward function is very difficult. And there is a long history of studies on the policy gradient theorem that tries to, that give us ways for us to evaluate this gradient using just observation of the state and the actions. And so we are going to use these approximations parameterized by a forgetting factor called lambda, which is a number between 0 and 1. And it is, as we're going to see in the analysis result, is going to trade off between the variance and the bias of the algorithms. So using these approximations, it motivates us to devise the following online update. Yes. So the online update says that we're going to accumulate this gradient of the conditional distributions, and we are going to, and then we are going to update the policies according to the gradient evaluated at this point. So we can see that equation 2b here becomes a stochastic approximation step with non-IID drift and with a biased mean field. So the prior works has only established the asymptotic convergence for such an OnI policy update, and we have a non-asymptotic result for such. So there has been many related works regarding stochastic approximations, thanks to its close relationships with SGDs, which which is widely used in optimization societies. So actually, in our paper, we studied 2 different cases for the stochastic approximation schemes, which can be categorized according to the different cases for this noise between the drift and mean field. So in the case when this is martingale difference, the landmark paper was actually written by Gardimi and Lan in 2013, which studies the non-asymptotic convergence, and we extend that to the biased settings. But what this talk will focus on is the second case, where we have a state-controlled Markov noise, as we have discussed about, where the non-asymptotic analysis is much more, the result is much more scarce. So the main result here, I just summarize this in a rather complicated theorems, but bear with me here. So the main result basically says that as long as the Markov chain underneath the SA scheme has some sort of smoothness properties with respect to the eta, the parameters, then if I set a decaying step size that grows as 1 over square root k, then we have a convergence to a biased stationary response at a rate of 1 over square root n with the log n. And here the C naught pops up as the bias of the SA scheme. So actually, if we apply this result to OnI policy gradient, we see that basically this is just a plug and play exercise. And we see that the OnI policy gradient update finds a stationary response at the following rate. And actually, you can evaluate all the precise constant, and they can be found in the paper. So we found 2 points here. So first of all, we realized that the gradient of this reward functions has 2 terms. One term that is actually a bias that decays if the forgetting factor goes to 1, and which also increases, and the other term actually increases if lambda goes to 1. So it gives us a variance and bias trade-off by setting these forgetting parameters. So since this is the last slide, I'm going to give you a very brief idea of how we prove that. So we follow a standard analysis approach of dealing with optimization problems in the non-convex settings. So using just the smoothness of the Lyapunov functions, we show that these telescoping sums, these black terms are easy to deal with. And the problematic part is that the last term, since we have a biased stochastic approximation schemes, this is not equals to 0, and it is not the martingale. So the idea is that we're going to exploit the Poisson equations, which says that there exist a certain measurable functions such that you can decompose the noise into these terms. And then we have a novel decomposition approach that allows us to control the sum of this inner product. So some takeaways here. So we show the non-asymptotic convergence rate for biased SA schemes, and with smooth and possibly non-smooth, non-convex Lyapunov functions with a non-IID drift. We show most of the case with the convergence rate of log n over square root n. And we also show applications of this new convergence analysis to different problems, such as online expectation maximizations and the OnI policy gradient that I just showed you. Thanks. And so a last joke here. So if you could go back in time, you could actually ask us a question at the poster. But otherwise, you can catch me until the end of COLT. Thanks.
Are we talking about the convergence of the final iterate here, or you do some averaging here?
It's some averaging here. There's some averaging involved in the convergence.
But you have a non-linear scheme here, so
yes.
How does the averaging make sense?
So the averaging steps actually goes by, so actually we see, so you might notice that this little n is different from the small n here. So actually before we start the iterations, we have to select a terminating criterion that is adaptive to the step size. And so we select when do we want to stop. And then the theorem tells you that in expectations, if you stop there, you're going to get this convergence rate. Yeah.
Thomas.
Oh.
I was wondering
It's probably not tight because we actually use a lot of sort of loose upper bound when making this. Can you say that again?
This bound would suggest that even with the best tuning of lambda, errors from go rays.
Oh, okay, okay. Yeah, actually, that's true. Yeah. Yeah, that's the price, kind of.
Discuss it with the post.
Yeah. Thanks.
All right, thank you very much. All right, and finally, let's